All right, good people. This video is on solving systems of equations. So we are going to maybe do some a little graphically, do some to see if things are inconsistent and dependent, if we can solve it by substitution, elimination, and maybe we can do some models, aka some word problems. So what is a system of linear equations? It is a collection of linear equations containing the same set of variables. And a solution to a system of equations is two variables is an ordered pair that satisfies both equations of the system. So let's say if we have ordered pair 2, 4, is this a solution to the system? Well, what you would do is you will plug in. So of course, this is the ordered pair, so xy. So this should be 2 plus 8 times 4 equals 234. So that'll be 2 plus 8 times 4 is 32 equals to 34. Well, 32 plus 2 is 34, so 34 equals to 34. So that's the solution to this one. And then let's say we plug in for the next equation. So 3 times our order pair is 2 for x minus 2 times 4 for y equals to negative 2. So 3 times 2 is 6. Negative 2 times 4 is a negative 8. And 6 minus 8 gives me a negative 2. So negative 2 equals to negative 2. So this is a solution. Okay, so they had to work in both of the equations. If they don't, then it is not a solution. So in solving for these systems of equations, there are three methods. Again, I said we can do it graphically, elimination, or substitution. So right now, we're going to do a substitution. Substitution says you solve for one variable and then you take that variable and replace it into the equivalent equation or the other equation, and then you solve for a particular variable. Once you have found that variable, then you find the OG. All right, you plug it back into the OG and you find the next variable or the second variable. Okay? And then you check the solution just as I did above, or you can check it by graphing. All right, so the first thing is we want to solve by substitution. So you determine what variable you want to solve for. Okay, now for me personally, I go with if a variable has no coefficient, if a variable or all of my coefficients are a even number, then that would be the equation that I would want to solve for. So I have 6x plus, well, not even, if all of the equations have something in common. So the first one, if we look at it, 3x plus 5y equals to negative 1, they all have nothing in common. But if I look at 6x plus 2y equals to 14, they have at least a 2 in common, or they're all even numbers. So let's try to use that. So 6x plus 2y equals to 14. In this case, it doesn't matter which one you solve for, but I just want to solve for y. So I'll subtract the 6x from both sides, and I'll be left with 2y equals to negative 6x plus 14. Divide both sides by 2, and then y will equal to negative 3x plus 7. Once we've solved for our variable, we plug this in to the other equation. So the other equation we want to plug it into is the 3x plus 5y equals to negative 1. So this would be 3x plus 5 times negative 3x plus 7 equals to negative 1. Okay, now we need to solve for x. So this will be 3x minus 15x plus 35 equals to negative 1. We combine our like terms, so 3 and 15 make a negative 12x, right? Plus 35 equals to negative 1. We need to subtract both sides by negative 35, and then this will give us a negative 12x equals to negative 36. divide both sides by -12, and x would equal to a +3. Now that we have our first variable, we need to find our other variable. And our other variable in this case would be y. You must plug this in into the original, right? Oh, that's a little bright on your eyes. So what is the original? So technically you can plug it in here, or you can plug it into either of the original statements. So I'm just going to plug it in here for time's sake. Y equals to -3 times 3 plus 7. All right. And this will give me y equals to -9 plus 7. So y equals to -2. So my solution to this system is going to be 3 and -2. That's bright on the eyes too. Okay. So our next method that we have is solving the equation by elimination. So elimination says that you are going to rewrite one or both of the equations so that you can eliminate one of the variables by adding or subtracting. So in order to do that, that means you have to multiply one or both equations by a non-zero number that will make the coefficients equal, all right? Except perhaps the sign. Then when you add and subtract them, then that means the elimination of the variables happen, and then we end up with one equation, right? Then once we have solved for that one equation, we plug it back into the OG, the original, of the second variable, and then we check for any remaining solutions, okay? Now, for a system such as this, we have 2x minus 4y equals to -7, and 5x plus y equals to -1. So we would want to determine which variable we would want to eliminate. So just off the top, I can tell you that if I'm looking at my coefficients, right? Coefficients are the numbers in front of the variable, right? 2 and 5, their least common multiple, right, would be 10, meaning that I would have to change this equation and this equation, right? But if I look at my y variable, I say, this has a -4 and this has a 1. This may be the better route to go because only I would have to change one of the equations and not both of the equations. So what I mean by that is now that we see that I want to eliminate our y, what we need to do is find our least common multiple, which is 4. So you multiply whatever 1 times whatever is going to give me that 4. So we'll multiply this whole equation by 4. So this should be 2x minus 4y equals to -7 on the top. And this should be a positive 20x plus 4y equals to -4 on the bottom. Then we're going to add these two together. One is positive, one is negative, so it will eliminate. Okay? So this will give me 22x equals to -11. So now we're going to divide both sides by 22, and x will not equal to a -11 over 22, which we can reduce to x equaling to -1/2. Now we take this number, right? X equals to -1/2, and you plug in to the OG. Who's the OG? The OG is your original function. I'm sorry, your original system. So it does not matter which one you pick. You can pick this one or this one. Okay, I am going to pick the top one because since I have a 1/2 and I have x equals to a negative, I'm sorry, since I have x equaling to a negative 1/2, I see that it can possibly eliminate with this 2. So we would do 2 times negative 1/2 minus 4y equals to negative 7. The 2's cancel out, and I'm left with negative 1 minus 4y equals to negative 7. I would need to now add a 1 to both sides, and negative 4y equals to negative 6. Divide both sides by negative 4, and now we see that y will equal to a positive 3/2. Now, where did I get 3/2? 6 and 4 have a 2 in common. 2 goes into 6 3 times, 2 goes into 4 2 times. So my ordered pair or my solution for this is negative 1/2 and 3/2. Okay, and another way again is for us to double check is to plug them back in, but for time's sake of the video, we won't do that, and double check to see if they are solution, or we can graph them. All right, and we'll talk about the graphs next. Graphically, so if we want to do something graphically, we set the equations equal to the slope-intercept form, right? And what's the slope-intercept form? Y equals to mx plus b. You then graph using the y-intercept and the slope. Again, the slope, if you recall from our last chapter, the slope is what? The m, right? And our y-intercept is the 0b, right? So before I get to graphing it, I want to talk about the different type of graphs, right? So if we're looking at these graphs and we see that we have one unique solution where the two lines intersect, such as here, then we can consider these to be independent. I forgot to write the word independent solutions or systems. That's really what we really call them, independent systems. All right, or consistent, and we can say consistent. All right, systems. All right. If the two systems or the two equations are parallel, such as these lines right here, then we consider the system to be inconsistent. Okay, and that it has no solution for our system of equations, and that is because they never intersect. Now, the last one is if the graphs are the same line, meaning we have the same exact line in the system, then these systems are considered to be independent. I'm sorry, dependent, meaning that one line depends upon the other, such as the example here. 3x minus 2y equals to 4 is the same thing as 6x minus 4y equals to 8. These two systems are dependent upon each other. Okay, so the very first thing is before we get to graphically 100% verifying, it says use use elimination method to solve the following systems if possible. Verify the solution graphically. So what we will need to do is if we want to do this by elimination method, we would have to determine which variable we would want to eliminate. Do we want to eliminate x? Do we want to eliminate y? So in this case, I guess because I've been doing y the whole time, we can go for the x this time, just so that you can see. So if I look at this and I look at 2 and 4, I have to say what is the least common multiple between 2 and 4? Well, the least common multiple, or the LCM between the two, is actually 4. So that means in order for me to get this 2 to become 4, I would need to multiply that by 2. But I don't, again, just do it for just the first term. I do it for the entire equation. So 2 times 2x is going to give me 4x. 2 times 5y is going to give me a negative 10y. And 2 times 7 is going to give me a 14. And then we have 4x minus 10y equals to 14. Now, we can pretty much see right here, even before I get to change something here. If we're doing it by elimination, if I add these two together, nothing would eliminate. So that means I have to change the sign. So I really should have been multiplying this by a -2. Okay? So this will now become a -4x. This becomes a +10y. This becomes a -14. So now when I add everything together, 0 equals to 0, right? So if you could not tell, but they were technically the same line, right? Meaning that there's going to be infinitely many solutions and they are a dependent system. So if I go to my Desmos, GeoGebra, right? And I put in what we had, 2x, right? Was it minus, Miss Parker, 2x minus 5y equals to 7. That's one. Then we're going to add another one, an expression. Oopsies. All right. And then we have 4x minus 10y equals to 14, right? If I blow this back up, look at our equation. Even though I've graphed them both, equation 2 and equation 1 are actually the same exact line, meaning again that these are dependent solutions. So, infinitely many solutions. Sorry.